On the first day of physics camp, we walked in and we had to go on an elevator up to where we were supposed to meet in the conference room for what we're supposed to do for physics camp. And sometimes going into an elevator is not only awkward, but it also makes you feel kind of funny. We went into the elevator, me and my friends, Peyton and Marianne, and we were talking about how you feel lighter when you go down in an elevator and heavier going up. And so in physics terms, because we're in physics camp, each of us would have a different apparent weight if they were to stand on a scale that might be in the elevator if it was accelerating. But while we're going up and it's slowing down, it'll still feel heavier to us, but it won't be as heavy as if we were going up and accelerating. And if we're going down and accelerating down, we'll feel lighter than if we were going down and then starting to slow down, because then as it starts to slow down while going down, the normal force is pushing up on us and decreasing our apparent weight.
On the first day of physics camp, my friend Marianne told me that she had been in a car crash on her way to camp. Well, what happened here? A myriad of forces are at play. The car was driving straight, and the car on the right accidentally started driving in the wrong lane. At this point, we have two cars of about equal masses heading towards each other with velocities in opposite directions. This is the recipe for a collision, in which two objects meet and exert forces on each other. The wreck was caused because each car had too great of a momentum, P equals mv, in order to stop soon enough to prevent a collision. The greater the momentum, the longer the stopping distance, or how long it takes for an object to accelerate to 0 meters per second. Stopping distance is also affected by friction, a force that opposes all motion. Perhaps friction wasn't great enough to aid the car in stopping in time to prevent a crash. Before she tragically crashed, Marianne was turning on an unbanked curve, where a friction force points towards the center of the curve, enabling the car to complete a safe turn. Without enough friction, the car would swerve and potentially crash into the ditch on the side of the road.
One reason that Marianne probably survived was because of the invention of a crumple zone and a bumper, to where that the front of the car will collapse and not throw the engine into someone's lap, and increasing the time of impact even if the force of impact is the same, reducing the overall momentum. I was vlogging earlier while walking, and then I forgot my calculator, so I had to run and go get it, but Peyton had been behind me, and so when we watched the video back, Peyton realized that we could use it to calculate our collision like we had learned in physics.
Marianne and I hadn't seen each other in a while, so when we collided into our weird hug, we represented a total inelastic collision. Of course, this would be in a perfect world scenario. According to Newton's third law, Marianne and I exert equal and opposite forces on each other. After the collision, we are one mass with the same final velocity, represented by the equation ma times VAD plus mb times VBD equals VA, the final velocity, times our combined masses, ma plus mb. This equation represents the conservation of momentum. I was taking a walk in the woods at physics camp, studying like a good student, when a fellow campmate rudely bumped into me. We bounced off each other after our collision, representing an inelastic collision if it were a perfect world scenario. Our conservation of momentum could be calculated using the equation ma times VAD plus mb times VBD equals ma times the final velocity of A plus mb, the mass of B, times the final velocity of B.
These different types of collisions that we found in our footage seem really cool, because that we were able to pick that out from what we learned in physics camp. We didn't have any case of an elastic collision, but remember, that's where energy and momentum are conserved throughout the collision. And that is the conservation of momentum equation, isn't it, that you're using to calculate. Also, things are in an isolated system where no external forces are being applied, and both objects are moving towards each other in opposite directions in linear momentum. With all the cool stuff that we learned in physics camp, we decided to try a few in real life and see what happened.
So if you have a projectile, it's an object that moves both horizontally and vertically above a planetary object, and it's only under the influence of gravity, so we can consider it in free fall. The only acceleration it has is vertical, and there's two types: a horizontally launched projectile and a level-to-level launched projectile.
In a type 1 projectile, there is a negative vertical displacement. In a type 2 projectile, there is no vertical displacement. For both projectiles, you will have to use delta x equals the initial velocity of x times time in order to find the horizontal displacement.
And we also need to remember that vertical acceleration that it has is the acceleration of gravity, g. Remember that. It's used, and the force on it is the mass times the acceleration of gravity. And the initial velocity is also the launch velocity, and the launch velocity is just made up of the vertical and horizontal velocity components. It's something we should remember. While we're watching this projectiles, is there any way for us to measure out the angle for maximum range of a level-to-level launch? You know, it's 45 degrees, and the range is like how high it'll go. I guess not really, huh? That's okay. My dogs came to see me today. My mom had to bring me my inhaler because I left it at home, and all this exciting physics is making me short of breath. So she brought the dogs with her so they can get out of the house, because obviously they were missing me. They started at an initial position of about 50 meters away, and they were supposed to run towards me, but they instead took off away to go say hi to the other physics students. I saw them running away, and I was thinking about how they represented some things that we learned at physics camp involving displacement and velocity and motion diagrams. I decided to draw them and calculate their acceleration. I knew their initial velocity was 0 because they started at rest, but I didn't know what their final velocity was when they reached the people they were going after, because I didn't have a radar gun on me. But I looked up what the average velocity for my dogs, or the average speed for my dogs are, and their Shih Tzus, which was 15 to 20 miles per hour. They ran pretty fast, so I could say that probably their average velocity or speed was 20 miles per hour. The difference between velocity and speed is velocity is a vector. It changes with direction even if the actual magnitude hasn't changed, but the average speed is just based off how fast they're going. It doesn't change with the direction. The velocity that I'm using to calculate this is their average velocity, not their instantaneous, because I don't have a radar gun to measure what it was at the time they ran into the people. So their overall displacement was about 50 meters. I worked out the problem using my kinematic variables and equations and motion diagrams and cube pictures, of course. Their acceleration ended up being 0.2. The dogs did experience a change in velocity/acceleration since both are vectors and depend on direction when they turned the corner to head towards the people. This was my motion diagrams of the dogs. You can see how the arrows start small and start increasing. That's because they had to gain speed, and it means they were accelerating. Here were my choices of all of the potential kinematic equations that I could use for constant acceleration. This one doesn't have velocity, this one doesn't have change in x, this one doesn't have time, which is why I used it, and this one doesn't have it.
In this clip, you can find impulse, which is the change in momentum. As you see, one ball seems dead and the other one seems bouncy and happy. The ball that rebounds off the ground actually has more impulse than the one that collides and stops. To find impulse, you multiply force average times change in time or mass times change in velocity. The ball that rebounds has initial and final velocity. To find the impulse, you add these two velocities together and multiply by its mass. However, the one that stops and collides only has one velocity, so you multiply the mass and that one velocity together. When comparing these two, the one that rebounds has a greater impulse since you add the two velocities together.
Acceleration.
Inclined plane, the angle of the plane is considered. If the object is not accelerating, then the net force equals to 0. This means normal force equals to the weight cosine theta and friction equals the force being applied on the object. However, if the object is accelerating up or down, this means there's an unbalance of forces. Therefore, the force being applied on the object is greater than the friction, and in both scenarios, normal force equals to the weight cosine theta because the object is not accelerating vertically.
And something also that I just thought about that we could say if this ever comes up in the physics battle is that this object has a lot of inertia because it's not moving and it's remaining unchanged. So you're saying in this picture, since the box is not accelerating up, down, left, or right, that all the forces are in equilibrium and there are no... According to Newton's third law, during an explosion, each object should exert forces of equal magnitudes and in opposite directions on each other. In other words, for every action, there is an equal and opposite reaction. The total momentum of the system is conserved in an explosion. For example, when a bullet fires, the bullet shoots forward while the gun kicks back. Since momentum is conserved and equals P equals M times V, which is momentum equals mass times velocity. Having a gun more massive than its bullet is important. The more massive the gun, the less velocity, so slower the kickback. Unbalanced force.
In this scenario, work, energy, and power can all be solved for. When holding a book and pushing it up on a desk, work and energy is involved in this scenario. Work is defined as force times distance and can be categorized into positive and negative. Because you are pushing it up with the palm of your hand and the book is traveling up, then the work done by your hand is positive work, since the force applied by your hand onto the book is up and the motion of the book is also up. However, if you were holding the book with the palm of your hand and setting it down onto the floor, then it would be negative work, since the directions are opposite. Once the book is set on the table, then the book has potential energy, work that has not been done yet, and is not. When you are moving the book with your hand, the system has kinetic energy because it is in motion. Power can also be calculated in this scenario. Power is the rate of doing work per time and can be found by work over time or the change in energy over time.
I saw this sign while walking through physics hall today at physics camp. I decided that I thought it looked really cool and I could probably do some of the motion free body diagrams on it, and so I decided to calculate it out in my head. I wasn't able to get the angles, but I got a general thing of it, and I thought that was pretty cool. The tension is pulling on the corner of the sign. The vertical components of the force of tension, T1 and T2, are equal to the weight of the sign. If not, the sign would float up or fall down, but that is not happening because they are obviously equal. And then the horizontal components of T1 and T2 equal each other, therefore they're balancing and not having one sway to the side.
At the carnival, we all decided to ride the roller coaster. At the top of the first ramp, potential energy is the greatest. At the bottom of the ramp, kinetic energy is greater than potential energy. However, if the height of the first ramp isn't large enough, the cart won't have enough energy to make it through the loop. Thankfully, this wasn't the case when we rode the roller coaster. Our cart made it all the way through the loop and to the end of the track. All the physics students decided to take a trip to the local carnival on their day off to apply all their nerdy and geeky skills to the real world and have some fun. So here we have a picture of us all on the Ferris wheel. I'm about to get on the Ferris wheel, so right now I'm feeling my true weight, which is just my mass times the G value, gravity, 9.8 meters per second squared. Michaela's at the bottom of the Ferris wheel, so she's feeling heavier than normal because right now her normal force equals mg plus ma, where a is centripetal acceleration or tangential velocity squared divided by the radius of the wheel. Marianne, however, is enjoying the lovely view at the top of the Ferris wheel, so her normal force equals mg minus ma, where a is also centripetal acceleration. And even though the Ferris wheel is taking part in uniform circular motion, so they're all going around at the same speed, technically they are accelerating because the direction of their velocities is changing while they're moving.
On that last roller coaster, when going down that big hill, I got this really funny feeling like I was weightless or something. Isn't it crazy that that's because our internal organs are free falling and have no support until we hit the bottoming out curve and our stomach drops? is so weird. The reason this is happening is because of g-forces, and g-force is, as previously said, the acceleration of gravity. And then the reason you feel this weightlessness is because there's the creation of a force greater than the force of gravity, which is changing your velocity. Also, while at the carnival, we went on the bungee jump ride. Our teacher told us that a bungee jumper is similar to a mass on a spring, so that when you pull down the spring, and then the spring pulls back up and down in shorter and shorter increments as energy is lost. The same thing happens with a bungee jumper, because the elastic rope is essentially the spring for the bungee jumper. He gets pulled down with his weight, and then he gets pulled back up by the tension, and then down with the weight again, and up with the tension, and that goes back and forth, and then the loss of energy makes it smaller and smaller. Understand? So we all thought as a group it would be good for us to record videos of us figuring out how to work some of the problems, and so I thought I'd include that in my vlog today. The ballistic pendulum is an example of a totally inelastic collision where the bullet embeds itself into the block and causes it to swing up because it's attached to a string. The momentum of the system is conserved, and in the system's initial state, only the bullet has momentum, and in the final state, right after the collision, both masses have the same velocity. A series of conservations of momentum equations can be used to solve for values such as the mass of the bullet or its initial velocity.
One of the things that we learned at physics camp was Atwood's machine. It's a pulley system that consists of two objects of mass connected by a massless string over a massless pulley. In order to find specific forces going on the system or on the part, such as friction and normal force, you have to calculate the sum of forces both parallel or perpendicular to the system and the part.
Graph A and Graph B are position versus time graphs. Graph A shows a constant velocity. The velocity is the slope of the line. Graph B shows an increasing velocity. Graph D would match up with Graph A since it's a constant value for the velocity over time. Graph C would match up with Graph B since the velocity is increasing over time. For velocity versus time graphs, acceleration is the slope of the line. Graph D does not have an associated acceleration graph because its slope is 0. Graph C's corresponding acceleration graph is going to be Graph E, because the slope of the line is constant, so it means that there is a constant acceleration. And then Graph F represents an increasing
Okay, so now talking about gravity. So these are two objects. We're going to pretend that this is the moon and this is the Earth. Obviously, the Earth has more mass than the moon does. So now there's this distance between the two planetary objects that we're going to label r. And you have the equation Fg, force of gravity, equals g, gravity constant, times m1 times m2 over r, this value, squared. So basically this reads, the force of gravity equals the gravity constant times the two masses divided by the distance separating them, squared. And what happens here, if you double the distance between the two objects, you're going to end up fourthing the force of gravity, which makes sense because if you double the distance, you'll be creating a greater r value. And so then you'll be dividing by a large number, meaning ultimately you'll have a smaller f of g value. However, if you half the distance between the two objects, so if we imagine this r becoming shorter, while keeping the masses of the two objects constant, then you will end up quadrupling the gravitational force, because in that case, you will have a smaller r value. And because you'll be dividing by a smaller r value, you'll end up getting a greater fg value. Now let's pretend that the distance between the two objects remains constant, but we're going to change the mass of the moon and the Earth. So now the moon is going to get this large, and we're going to make the Earth this massive. New mass for that, and a new mass for that. Since the r is determined from measuring from the center, there we go. Okay, so if you keep the distance between the centers constant, which is what's going on here I'll write that. Distance between the centers of the two masses is constant, but you increase the two masses of the objects, then you will end up with a larger Fg value. So basically, when you're in space, every object in space is going to exert some gravitational force on the other object. So by manipulating these two variables, the r, the distance between the centers of the two masses, or changing the masses of the objects themselves, you will get different force of gravity values. Okay, so here we're talking about orbital period, and orbital period is the amount of time that it takes for an object to complete one orbit around another object. So I'm talking about astronomical objects here, so we have like the moon and the Earth because it orbits around the Earth, or the Earth orbiting around the sun. So we have two different equations here that deal with orbital period. They both deal with the same relationships talked about in Kepler's third law, which just means that these two variables are proportional. according to Kepler's third law, so t actually represents orbital period, and when you solve it, so this equation simplified is just so you can solve for t. It ends up being in seconds, but most of the time you can convert it into like days or Earth years. And the r right here is the radius, but it's actually the radius of the object's path, or for instance, if you have Earth right here, and let's say that this is the moon, here is one Earth radius, but then you also need this distance between the Earth and the moon, and this amount together is the r that you'll be using to solve the equation for orbital period. So if you have the distance from the Earth to the moon, you add that to one Earth radius, which is about 6.38 times 10 to the 6 meters. Okay, so let's talk about the units of this equation. The mass is the mass of the object that is not doing the orbiting. So if we were solving for the orbital period of the moon, this would be the mass of Earth. If we come back here, the reason this says the mass of the sun is because this equation can be used to be solved for the orbital period of any of the planets in our solar system that orbit around the sun. So we could find the orbital period of Earth, we could find the orbital period of Saturn, of Mars, Venus, any of the planets. And notice how the orbital period does not depend at all on the mass of the object that is actually moving. So if we have the moon here, and let's say we had, I don't know, a satellite at the same distance from the center of the Earth as the moon, the two objects, even though we're assuming the moon to be much more massive, would actually have the same orbital period. So back to here, we're going to look at units. So if you have the mass of the Earth, or the mass of the sun in this case, it needs to be in kilograms. And this is all because of the gravitational constant g, which is equal to 6.67 times 10 to the negative 11, with really weird units, which is Newton meters squared divided by kilograms squared. So we're trying to keep our units the same, that way we can use this constant, so our units will cancel out, and eventually we'll get our answer, orbital period, in seconds, which we can then convert into other units, such as Earth years, Earth days, things like that. So kilograms, kilograms. Here, we want the r value to be in meters, 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 and then 4 pi, so that's not going to have a unit. Oh, and up here, anything orbiting the Earth has the same Kepler constant, which is k, and anything orbiting the sun has the same Kepler constant, which is also k. So this goes back to the notion about the mass of the moon, or the mass of the orbiting object, not affecting its orbital period. And overall orbital period, when you're using these relationships, or when you isolate t, you're assuming that it's going to have a circular path instead of an elliptical path. Okay, so what's here are just comparison problems. After we've manipulated the mass and the distance between the centers of two planetary objects, we made up a star and moon. We have these given masses for them. The units are coming from the universal g constant, or gravity constant, of this number. So we want all of our units, except for newtons, since we are solving for a force, to eventually cancel out. So here's the original problem. We kept all the original values, mass 1, mass 2, divided by the r value squared. We get this number, 3.56 times 10 to the 21st newtons. Now this time, we doubled r, so these two objects, or these two centers, are double the distance away from each other, so it would be about right here. And we plugged in the same masses, plugged in r value that was double of the original, and solved. 8.89 times 10 to the 20th newtons. Now what's important about this is that we doubled the distance between object centers while keeping their masses constant, and we got a new FG value that is 1/4 of the original FG value. So if you multiply this number by 4, you'll get the original. Now here, we changed the mass. So we kept the distance between their centers the same, but we doubled the mass of both objects, and we got 1.42 times 10 to the 22nd newtons. So if you increase the mass of the objects while keeping the r value the same, you will also increase the force of gravity between the two planetary objects.
At physics camp, we were going to have a physics off. And so me, Peyton, and Marianne decided to study the various concepts that may or may not come up in the physics off, so we can make sure we can beat all the other physics students groups at physics camp.
In this clip, you can find the spring constant and the elastic potential energy. The spring constant is used to find the force needed to extend or compress a spring, and can be found by Hooke's law, which is the force of the spring equals the absolute value of the spring constant times displacement. Whether you extend or compress the spring, you increase the elastic potential energy of the spring.
While at camp, one of the counselors told us a story of a rogue satellite that had left its orbit around Earth. In order to leave a planetary object, you have to reach escape velocity. This can be calculated using the equation gm, representing the mass of the planetary object in kilograms, divided by r, the radius of the planetary object, equals 1/2 ve squared, where escape velocity is in meters per second.
Terminal velocity is the highest velocity attainable by an object as it falls through a fluid, which includes the atmosphere. When the force of gravity is equal to the force of air resistance less drag on the object, it's in constant velocity, also terminal. Physics off, I think it's very important that we all understand the basic principles of physics, because obviously it's a physics off, and so that means I think we should know Newton's laws, and we know the third one, we already went over it earlier, but so Newton's first law, remember, is an object will remain at rest or in uniform motion unless acted upon by an external net force. And then Newton's second law states that the acceleration of an object is dependent on the two variables, a net external force acting upon
upon the object and the mass of the object, we can derive from this law the equation F net equals ma. Force an object can exert is dependent on its mass and its acceleration.
How do you feel about leaving physics camp?
I'm so excited but sad at the same time.
Bittersweet?
Yeah.
It's bittersweet for me too.